All right, here's the solution for the final exam review over digital topics, problem number 3. Okay, in this problem we're talking about the differences between the z-plane and the s-plane, and if you'll recall, when we were looking at solutions to differential equations, the important function for the homogeneous solution was e to the st, okay, and the corresponding counterpart in the discrete time was z to the n. All right, so the answers to this question really hinge on these two things. This is the function we used for the homogeneous solution in both domains. Okay. So, when I start thinking about sinusoids, what value of s will generate sinusoids from this function? Okay, so if we make s equals j omega, we'll put c for continuous time, then what we get is e to j omega ct, which is cosine omega ct plus j sine omega ct. So here we are, we have cosine showing up, and so if we just take the real part, we can model the effect of a cosine of frequency omega c. All right, so I'm letting s equal j omega c, and so over here in the s plane, that gives me the j omega axis. Okay, so this is the frequency axis in the s domain. All right, so let's do the same thing over in discrete time. All right, the form of the solution for the homogeneous solution for difference equations, we've talked about that. That's z to the n. Okay, so how would I get a sinusoid out of that? Well, we've talked about that before as well. You let z equals e to the j omega. Okay, so that would give me, plugging in, cosine of omega n plus j sine omega n, and as before I take the real part and I get back a sinusoid. Okay, so this relationship tells me what values of z give me what I'm calling the frequency axis. It's not really an axis, it's really the unit circle. You may remember from trig that the unit circle is traced out by cosine of omega, sine omega. So x is cosine, y is sine. That's exactly what this expression is giving you. Okay, so this is a unit circle. The radius is supposed to be 1. This is a terrible circle, but you get the idea. Okay, so let me put it in red. This is what we call the frequency axis in discrete time, even though it's really not an axis, it's a circle. All right, so that's the z-plane, or z-domain. Okay, so that answers the first question. All right, so related to that is the issue of stability. All right, so we're wondering about BIBO stability. Okay, well, skipping some of the mathematical details, what we need for stability is we need the term e to the st to shrink to 0. And the reason for that is the homogeneous solution has components based off of e to the st. If the homogeneous solution doesn't decay to 0, the system's going to be unstable. Okay, so what we need then is the negative sign on the exponent to force the signal to somehow die out. It might wiggle and die out like this, but it still needs to die out. Okay, so that means we need, for stability, S, all the poles have to be, I should say poles. All the poles have to be left half plane. Okay, so what's the counterpart over here? We're looking at z to the n, and we need that to vanish to 0. So if I have the magnitude of z less than 1, then as I light z to the n, as n gets large, then absolute value of z to the n vanishes to 0. Okay, so that means that everything inside the unit circle is what gives you stability over in the z domain. For the s domain, it was everything in the left half plane. Okay, so hopefully those make some logical sense to you. All right, so what we've done so far is we've taken care of frequency axis, we looked at conditions on stability. Now the question is, what about DC? Well, DC is the same thing as 0 frequency, all right? So you let omega equal 0. All right, so what happens when I plug in omega equals 0 in the S domain? Well, if you plug in omega c equals 0, then you get S equals 0. So the origin is where you get DC. That's the value of S that corresponds to DC. All right, how about over here in the discrete domain? I let omega equal 0. I plug that in. I get e to the 0, which is z equal 1. All right, so right here is the value of z that represents DC. Okay, so that takes care of part D. Now let's look at the highest frequency in a discrete time system. All right, well, I'm just going to state the answer. I think we know that if we sample a signal, we need to sample it at least twice the highest frequency. So it turns out the highest frequency that can be present is fs over 2. That's the highest frequency present from the continuous world when it gets discretized down into the digital world. Okay, so let's think about that. We talked about converting between continuous time frequency to discrete in a previous problem. And so what we said is to get to the discrete time frequency, we take the frequency and we divide or multiply by 2 pi and divide by fs. Okay, by the way, this is in hertz. All right, so I converted this to radians per sample. Okay, and so we look at this and these things cancel and I'm left with pi. Pi radians per sample is the highest frequency. All right, so if I'm thinking of things in terms of frequency, this would be like cosine pi n. And if you think about it, this is a discrete signal. That's the fastest this can possibly wiggle. You know, it goes between 1 and -1. So that's the highest frequency present in a digital signal. All right, so that's the answer to part E.